Polymers are viscoelastic materials. In other words, their mechanical properties have both elastic and viscous components. Their response to an applied stress depends on the timescale of the experiment. The phenomenon of creep, which is the increase in strain with time at constant applied stress, and stress relaxation, which is the decrease in stress at constant strain, are examples of time-dependent properties. The simplest models for the deformation behavior of an ideal material are those of Hookean linear elasticity in the solid state and Newtonian linear viscosity in the liquid state. The end point of elastic deformation is either fracture or plastic flow, with the latter taking place at a constant yield stress in the ideal case. Whilst the behavior of many real materials does approximate to these idealized models, that of polymers deviates markedly from them. In particular, their solid-state deformation is time-dependent and nonlinear, and so resembles some combination of elastic and viscous responses, whilst their melt rheology is also significantly nonlinear. To start with, let's consider polymer behavior in the context of the idealized models of elastic deformation and of viscous flow. Elastic and viscoelastic behavior. When an elastic, not elastomeric or long-range elastic material is stressed, there is an immediate and corresponding strain response. When the stress is removed, the strain also returns to zero. So in a perfectly elastic material, all the deformation is returned to the forcing agency. If this energy had not been stored elastically, then it would have been dissipated as either heat or sound. Tires squeal, and the heat buildup in the sidewalls of car tires are good examples of such dissipation. If the material is linear and elastic, then the applied stress sigma directly proportional to the strain epsilon. Then, for simple tension, sigma equals E times epsilon, where E is a constant known as Young's modulus and is considered to be a property of the material. For polymers, due to time dependence and nonlinearity, E is not a constant, and the term tensile modulus is used to reflect this. In the stress-strain curves for PS, HIPS and two types of rubber polystyrene apparently obeys Hooke's law, HIPS yields and necks before failing. By contrast, rubbers exhibit long-range elasticity and fail only at many 100% strain. So some plastics like HIPS yield, but others fracture in a brittle manner like polystyrene. Rubbers do not yield, but at high strains some of them crystallize and hence stiffen. When the stresses are removed from a polymeric material before fracture, the strain recovery path is not necessarily identical to that of the loading part of the deformation cycle. So energy must have been dissipated during the deformation of such materials, another indication of deviation from perfect elasticity. Both the deformation and the subsequent recovery are time-dependent, suggesting that some part of their behavior is viscous. In fact, solid polymers show a combination of elastic and viscous behavior known as viscoelasticity. The degree of viscoelasticity is strongly dependent upon the temperature of test and the rate at which the polymer is deformed, as well as such structural variables as degree of crystallinity, cross-linking, and molecular mass. Viscous behavior. Viscous flow is not recoverable. When the stress is removed from a viscous fluid, the strain remains. Hence, the work energy is not returned to the forcing agency and has to be otherwise dissipated. For a linear viscous material, the rate of change of shear strain with time is directly proportional to the imposed tensile stress sigma. The viscosity is also directly dependent on molecular mass, and so inversely related to melt flow index. These factors are thus of direct importance to a processor or molder. Viscous properties dominate during the earlier stages of processing, but elastic effects are also important. Molten thermoplastics are obviously highly viscous, as are partially polymerized and uncured thermosets and masticated and unvulcanized rubbers. However, Observable features such as the swelling of extrudates as they leave dies are manifestations of melt elasticity. In essence, elasticity in molten polymers arises from the entropy factor or the tendency of the macromolecules to coil into their configurations of maximum disorder. This is in opposition to the stretching which occurs as the material flows under the influence of the stress field. Viscoelasticity and master curves. An immediate consequence of the viscoelasticity of polymers is that their deformations under stress are time-dependent. If the imposed mechanical stress is held constant, then the resultant strain will increase with time, i.e., the polymer creeps. If a constant deformation is imposed, then the induced stress will relax with time. Stress relaxation. There are many examples of products which creep in service. For example, the plastic tub of an automatic washing machine will successively creep and recover as it is loaded and unloaded several times during the washing cycle. Viscoelastic stress analysis during the design of the tub ensures that the maximum strain due to this loading pattern is well within the strain limits for the material and the application. The creep and stress relaxation properties of a polymer can be described by the time-dependent moduli E, C, and ER. The creep modulus is the ratio of an imposed constant stress to the time-dependent strain, while the stress relaxation modulus is the ratio of the time-dependent stress to an imposed constant strain. Practical examples of the need to design for stress relaxation are in seals where the sealing force must remain adequate under conditions of constant deformation, or when a metal peg needs to be held in a plastic block by push-fitting into an undersized hole. The oversized peg results in a constant hoop strain in the plastic. The corresponding hoop stress will decay with time, but must always be sufficient to hold the peg in place. Both creep and stress relaxation are factors that have to be considered in design, although they are not necessarily always deleterious. Time-dependent relaxation moduli ER is characteristic of the polymer concerned at a particular strain and temperature. It is the tensile stress relaxation modulus if the corresponding strains and stresses are tensile. Alternatively, if the strains and stresses relate to shear or hydrostatic changes, then the corresponding material parameters are the shear and bulk relaxation moduli, respectively. For polymers, the tensile modulus should not be referred to as Young's modulus. Young's modulus is the limiting case of the tensile modulus, when the induced strains can be considered infinitesimal and independent of time. Time-temperature superposition. For amorphous polymers above their Tg, there is a convenient approximation which makes experiments easier. It is known as time-temperature superposition, and it relates time to temperature for viscoelastic materials. A sequence of measurements of ER is performed at different temperatures at a fixed initial strain. The timescale might be limited between several seconds and, say, 100 hours. As the material passes through the transition region, the modulus drops rapidly. The material is becoming rubbery in its response to the applied stress. The onset of true elastomeric behavior is marked by the so-called rubbery plateau. This is followed by another steep fall in modulus, where viscous flow occurs as the temperature is raised further. Effects of structure on viscoelasticity. If a single measurement of ER is taken at an arbitrary but fixed interval of time, say 10 seconds, then it will vary with temperature in a way rather similar to the viscoelastic master curve. The effect of lightly cross-linking the material is to eliminate flow of any kind, extending the region of elastomeric behavior to higher temperatures. Heavier cross-linking will move the rubbery plateau upwards, and the same net effect is achieved by crystallization. Although atactic PS is inherently non-crystallizable, the isotactic form can crystallize, and its melting point, Tm, is about 230 degrees Celsius. Molecular mass also affects the stress relaxation spectrum, particularly at intermediate and higher temperatures greater than 100 degrees Celsius. For high molecular masses, only the rubbery plateau and viscous flow regions differ markedly. The glassy and transition regions are unaffected. Increasing molecular mass clearly improves some mechanical properties, but nowhere near as effectively as crystallization. Dynamic mechanical properties. Viscoelasticity is not experienced just under quasi-static conditions, that is, when the imposed stresses and strains are constant or change only slowly. Polymers, and particularly rubbers, are often deliberately selected for products which are to be subjected to dynamic mechanical loading. Tires are an obvious example where the unique high-strain elasticity and energy-absorbing qualities of rubbers make them the natural choice of material. Stress analysis involves the use of the frequency-dependent dynamic moduli of the polymers. Stress analysis concerned with the dynamic mechanical properties normally assumes that polymers are linearly viscoelastic. The strain response lags behind the stress by the phase angle, owing to the viscous component of the material. Some, but not all, of the energy stored during the deformation of the material is dissipated. Since the material is assumed to be linear, the stress is proportional to the strain at all times, that is, sigma equals E epsilon, but E is a function of the frequency omega. Because the stress and strain are not in phase, E must be treated as a complex function. From the definitions of the dynamic moduli and by manipulation of the linear relationship between the sinusoidal stress and the corresponding strain response, the phase angle delta can be expressed as follows. Tan delta equals E double prime divided by E prime. Tan delta is commonly called the loss tangent or damping factor. E double prime and tan delta are the most commonly measured dynamic properties of rubbers, representing the elastic stiffness and damping or hysteresis properties respectively. Different rubbers will have different curves, and some care is needed in rubber product design to match the material with expected imposed frequencies. Fillers such as carbon black will also affect the shape and position of the damping maximum. At very high frequencies, omega equals 10 to the power of 10 to the power of 8 cycles per second, or hertz, rubber is very stiff with a glass-like modulus. At these frequencies, the polymer molecules do not have time to react in response to the forcing oscillations. The damping factor is then small, but it increases to a maximum value in the leathery transition region between the glassy modulus and the usual low modulus, which is characteristic of rubbers that are deformed slowly. Omega less than 1 cycle per second, or hertz. It is important to note that decreasing the frequency of oscillation imposed on the material is equivalent to increasing the temperature. Glass-like behavior is experienced at high frequencies. This is another manifestation of viscoelasticity, in which the effect of the 3 basic variables, time, T, temperature, T, and frequency, omega, on a polymer are all closely interrelated. Since decreasing the timescale of an experiment is equivalent to decreasing the temperature, so decreasing the frequency is equivalent to increasing the timescale and hence increasing temperature.